Good afternoon, everyone. I'm Gloire Rubambiza. I'm a PhD candidate in computer science at Cornell University. Today, I'll be telling you about Comosum, which is an extensible, reconfigurable, and fault-tolerant platform for digital agriculture. This is joint work with my collaborators at Cornell, Shiang-Wan, Sachille, Atapattu, Mueed, Rehman, José, Martínez, and Hakim Weatherspoon. We had a really interesting team of PhD students and undergrad, and then my co-advisor, Hakim Weatherspoon. So if you don't listen to me for the rest of the talk, I'll totally understand. So here's one slide to just give it all to you. This is pretty much 4 years of experience. We're trying to distill black box state-of-the-art systems down to classical ideas. And it's a new architecture that applies and advances the state-of-the-art to a new portfolio of system challenges. And we also took lessons from 18 months of deployment with 1 million sensor readings across farm types and cloud providers. So in terms of a roadmap, I'll give an overview of what digital agriculture is, because it may be a new term for some of you. I'll present the data and infrastructure challenges that are in working in this space. I'll briefly cover our design and implementation in Comosum and the decisions we had to make. And then I'll close off with a lot of lessons that we learned during our 18-month deployment and their broader implications for distributed systems. So to begin with, what is digital agriculture? Shepard et al. Described digital agriculture, or DA, as the growing ability to convert data into actionable insights to support decision-making in farms. Looking at the literature, you will see it described by some of all of these things related to data. First, it's the collection of massive sensor data in farms. It's transmission using on-farm networking. It's storage in cloud computing servers, processing it using various APIs and optionally AI. And then finally, we were trying to help farmers with the final goal of helping in the decision-making process. That is, for example, will a cow be getting sick in the next 24 hours, or are the plants water stressed? So that's digital ag. Now I'll cover the massive data and infrastructure challenges that motivated our work behind Comosum. What do I mean by massive data? Let me give you 3 examples of research projects that we have been working on at Cornell to demonstrate how DA is still emerging as an infrastructure. First, plant scientists need to understand lighting effects on plant growth to produce plants that will be more resilient to climate change. This requires collecting kilobytes each hour of data from moisture, CO2, and light intensity sensors and transmitting to the cloud for long-term storage and analysis. Our collaborators in animal science need real-time monitoring of dairy cows to facilitate early disease detection. This requires integrating each day megabytes of data from wearable and non-wearable cow sensors, sensor vendor software, and in-person data collection. Thirdly, we're working with plant pathologists that need fast methods to detect vineyard diseases and viruses that affect grapes, and if you do care about wine, also wine quality. This requires pulling and analyzing each year terabytes of data from NASA satellites and sensors that record hyperspectral imagery of rural farms. What do I mean by rural? Working in rural areas, there are a few infrastructure challenges that we have to deal with. That is, because of sparse population and geography, Hardy et al. Lists limited internet connectivity and public transportation as major challenges in rural areas. Hassan et al. Mentioned reliably unreliable power as a third issue. So then, it would be a valid reaction to say, why don't we give those farmers just 5G, Uber, and Chromebooks? Well, even if we can install 5G, social science has found that because of the scale assumed in technology design, rural infrastructure tends to be less built out, more prone to breakdown, and less likely to be repaired than urban infrastructure. This forces people in rural communities to have to repair their own equipment. But it's also hard to repair because the distance from urban areas limits access to repair parts. For example, I'm working in a college town, and I'm able to access Prime Day, 2-day shipping to get battery replacements. That may not be the case in a farm. So then we have to think about, there have been a few companies that have tried to address the first 2 issues, but they end up making the issues worse in 2 ways. First, by limiting access to their hardware, system software, and manuals, that is repair manuals. And secondly, by letting the farms pay for the equipment, collect the data, and then turn around and resell the data and insights back to the farmers. This is known as vendor lock-in. That is an arrangement where customers are dependent, that is locked into one provider, and it becomes difficult to move in the future because of technical and legal constraints. Vendor lock-in is similar to infrastructure lock-in, where it becomes hard to change the system or innovate on it once the direction is set. The point of this work then is that DA is still new, and there are companies which are trying to lock in different aspects, the data, the analytics, the networking, the infrastructure. But we would like to put the interests of farmers who usually operate on small margins first. So how do we do that? Well, the research question we're trying to address then is, how do we build data-intensive applications on top of unreliable rural infrastructure? The way that we can resolve a lot of these issues is by mapping the infrastructure challenges on the left to desired system features on the right. So first, when it comes to sparse connectivity, and unreliable power. We need sensor networks that can be reconfigured to fit different geographies and applications. We need low power sensors that can be able to reduce how often we have to replace the batteries. When it comes to the scale of technology and to simplify maintenance in remote regions, we need to be able to tolerate equipment failures, that is detecting the failures, pinpointing which equipment failed. Was it the sensors, the networking, was it the software, the analytics? And if repairs needed, we need to build a system with off-the-shelf parts so that we can be able to buy this in any hardware store. To avoid vendor lock-in, what we do need is open source Xware. That is hardware, firmware, software, APIs, and so on, which in turn will promote accessible data analytics. So then let us briefly look at how these challenges have been approached in the state of the art and why Comosum is needed. When it comes to the farm, the research on sensors has been too vast. We both know of sensors in vehicular networks, like self-driving cars, healthcare, wildlife tracking, like ZebraNet, for example. Now, we are interested in sensors that can be deployed in farms of varying sizes, such as temperature sensors, or cameras, or drones. But looking to the future and going beyond prior work, we're looking at 2025, where NASA is going to deploy new satellites, and they're going to be collecting a lot of farm data. So then we want to be able to support those because they're going to be streaming that data into the cloud. Now, thinking abstractly, whether we get the data from a physical sensor or from a NASA server doesn't matter. What matters is the bandwidth that we have. That is, how much data are we generating and how fast can we process it? Prior work has shown that sensor bandwidth can vary from 50 kilobits per second to 10 megabits per second. Why do we care about sensor bandwidth? This is because we're working with limited connectivity and limited bandwidth in rural locations. So then another thing to consider is how many sensors do we need? That may vary on the farm size, because farms vary from 400 acres to 5,000 acres and bigger. So then can we plug and play different numbers and types of sensors as the bandwidth changes without changing the overlaying software? Now, we've collected a lot of sensor data. We need to process it. We have two options here. The first is the cloud, which is the US National Institute for Standards and Technology, or NIST, defines as ubiquitous, convenient, and on-demand network access to potentially unlimited storage and compute. The second option is you can just store and process the data close to its data source at the farm edge. You can see that these two represent a trade-off. That is, with the cloud, we get more storage and compute, but it will take a lot of bandwidth to access, but we're limited in bandwidth. With edge computing, we can be able to have less storage power, but if we lose connectivity to the cloud, we can still be able to connect, like have disconnected operations. So then the third issue we have to deal with besides the edge versus cloud is that sometimes you have sensor vendors. In this case, they have a vendor lock-in issue where the sensor vendors will stream the data directly into their clouds. So then they would force us to either use their REST APIs to get the data, or they tell us where to dump it on the farm computer, and we have to deal with the cleaning and the processing. This complicated the design considerations again because it increases the data formats, the APIs, the libraries, and operating system dependencies that we have to deal with. So then we want to achieve the vendor neutrality. What do I mean by that? That is, we reframe the placement problem that is as a distributed cloud. That is a cloud consisting of the original farm or edge cloud, the public or core cloud, and then the sensor vendor clouds. We can't place workloads in the vendor cloud, but we can only get data from it. So then, in light of these challenges in the state of the art, we asked a more specific research question. Is it possible to build a platform that can be extended to new DA vendors and applications, can be easily reconfigured to support evolving sensor, network bandwidth, and cloud providers, and can tolerate failures in the base infrastructure? That's where our system, Comosum, comes in. Our general approach to Comosum is to enable the reconfiguration of sensors, cloud providers, networks, and applications. Therefore, we provide an extensible and flexible architecture that connects disparate hardware and software to collect and process farm data. I will move on then to dive a little bit deeper into the Comosum design, and then we'll cover FarmBIOS, which is an implementation of the architecture. So you can start looking at these images. This has been 4 years that we've been working on Comosum. And in this case, we tinkered with a lot of existing systems, and this including deploying things in our backyards during the pandemic because we couldn't go to the fields, and also doing tests at university farms to understand what bandwidth constraints do we have, and we can deploy new technologies like TV white spaces. TV white spaces is the image in the middle, where we're using TV channels, that is analog TV channels, for internet connectivity. So then, based on this extensive 4-year experience, we boiled the Comosum design down to two principles or two design concerns: a data plane and a control plane. Now, because of this inspiration from software-defined networking, or SDNs, Comosum also goes by the name of software-defined farm, or SDF. So Data plane and control plane. The data plane operates as follows. So we have sensor data, it's generated, and then it's sent to the telemetry modules that I've highlighted here. The telemetry module then notifies the analytics unit of there's new data. The analytics module is made up of storage and compute modules that we're building. Then the analytics module does the computation, generates a signal that says we need to irrigate the plant or whatnot, so that's sent back to the farm. Then, to resolve a lot of the vendor lock-in I mentioned, where operating system dependencies, data formats, API dependency, and so on, the modules simply pass bytes to each other, and it is up to the application developer to determine the structure of those bytes, which is pretty similar to the Linux file structure. So then the implementation can customize those modular objects to solve different set of real-world problems in digital agriculture, for example, in vineyards versus cows. Therefore, the data plane is extensible. When it comes to the control plane, the modules can be configured using reusable templates. You can think of a YAML file in this case. So then the templates are going to specify which modules should be deployed, where they should be deployed, and how they should communicate with each other. That is where they should be deployed in the distributed cloud, that is the edge, core cloud, and vendor cloud. Thus, the control plane gives us reconfigurability. So then when we put all these ideas together, the distributed cloud, the modular ideas of the modules we have, the compute, storage, analytics, and telemetry, then we put together what we call the Farm Basic Input-Output System, or FarmBIOS. This is because a lot of the state-of-the-art is incompatible hardware and software systems. They don't talk to each other. There's a lot going on in that figure, but I just want you to know how we reuse the SDN primitives to achieve our design goals of reconfigurability and extensibility. So if you're to build a Comosum instance, if you're to build an application for Comosum, you would have a reconfigurable control plane because you take your application configs and you deploy the requested modules, that is the modules you want to deploy, in the distributed cloud. So then the extensible data plane, what it gives us is that it's in charge of sending those bytes between modules, as I mentioned before. One extensible data plane component I would like to discuss a little bit further, maybe 30 more seconds, is the RPC protocol. That is because it ensures that the modules are network agnostic. What do I mean? That is, we have a FarmBIOS dispatcher that's going to be routing the messages between the modules, and the modules do not need to know if they're communicating over 4G, 3G, or TVY spaces. So then we'll now look at how we deployed and applied these ideas by looking at some applications and deployment experiences of the system. So we applied FarmBIOS to 3 motivating data challenges that I showed earlier before with the greenhouse, the dairy farm, and the vineyard. In this case, we named them WaterGuard, Cows on Fitbits, and WineGuard. And in case you have not caught on yet, we did have a lot of fun naming these systems. So now we look at how we deploy some of these systems. We call them FarmBIOS instances. So first is WaterGuard. WaterGuard is the vineyard disease detection system, which we built in collaboration with plant pathologists at Cornell. That is, you can imagine bringing this map to a vineyard manager to help them in decision-making, saying, these are symptomatic vines. So we use hyperspectral imageries from NASA and machine learning to predict virus with up to 84% training accuracy. And we're able to do this in a matter of seconds. The state of the art is you would take the leaves, you clip the leaves from the vineyard, you take it to the lab, and it takes days to find out if there's virus. For those few days, you're still spreading virus in your vineyard. Another thing to note here is that we deployed them in an edge cloud and in a core cloud. And what you can see here is that there's a difference of almost a minute. It shows the trade-off between having things at the edge versus in the cloud. We can do things faster at the edge, and we can be able to enable disconnected operations. So the next deployment we had is WaterGuard, which is the plant water stress alert system. So we deployed these 9 sensor hubs. Is the image you're looking, the second image from the left. And the sensor hubs have averaging about 8 sensors each, so 72 sensors in total. And we deployed it across a diverse network configuration. That is, we have 4G hotspots, TV white spaces, long-range radio, or LoRa, and edge devices. And this has been deployed in 2 edge clouds that I will show on the next slide. We deploy them at university test farms. So on the lower left corner, what you see is Edge Cloud 1, where we're serving our apple orchards. In Edge Cloud 2, we have that Edge Cloud is going to be serving, it's been serving hemp, corn, strawberries, and tomato growing experiments. In terms of increasing bandwidth here, you can see that the network starts with kilobits per second from the sensors. We go to megabits per second using TV white spaces to get to the Cornell campus. And finally, to the Azure cloud, where we're using a 1 gigabits per second Ethernet connection. Now, as shown in this plot, WaterGuard has been deployed for 18 months and collected more than 1 million sensor readings. The x-axis shows us the time series. On the y-axis, we have the external temperature of the sensors. You will note that one thing here is that the 4G connectivity was lost for a few days, multiple days during a snowstorm in February 2021. Until we restored the connectivity, the sensor readings were simply stored at the edge devices, which shows the value of storing things at the edge, at least temporarily, until we have connectivity back. But the analytics was affected by sensors, that is faulty sensors and human errors. Here again, we have a time series on the x-axis. The y-axis is the battery levels of 2 sensor hubs, where you'll see that faulty sensors in edge hub 2 ended up draining the batteries in 2 months compared to 1 year with edge hub 1. It took us 6 months of debugging to figure out that it was the faulty CO2 sensors. Sometimes you also have human configuration errors, and then you will have data which is being placed in the incorrect columns. What I'm trying to say is you can also have the same plot here, time on the x-axis and then temperature on the y-axis. You will also see that the sensor faults lead to data discontinuities. So we adapted the system to this issue through what we call active digital twin. A regular digital twin represents a process or physical process or object. An active digital twin would be sending us emails and texts when there's something that's not going right. The sensor is not reporting as we expected. So then, in our context, we twinned those sensor hubs so that we can be able to know when things need to be checked. Now, the Comosum really lent itself because of that telemetry actuation module design. And in this case, we're able to increase the system's fault tolerance, especially in a space where if you don't detect a failure, cows don't get fed, plants don't get watered, or in the worst case, you have to dig sensor boxes that are 2 feet of hardened snow in the middle of upstate New York. So the original goals were to provide an extensible, reconfigurable, and fault-tolerant platform. The platform evolved as we learned quite a few insights and limitations. First, extending the platform to new DA vendors comes with minor costs. That is, we're able to merge, analyze data from multiple vendors, but it takes about 50 lines of code to add a new script so we can be able to trigger the modules with new data. Secondly, we realized that the cloud surprisingly complicates our reconfigurability effort. For instance, in WineGuard, the Azure machine learning APIs were regularly being deprecated, and this made the reconfigurability problem much difficult. We heard a similar statement in the Sky Computing keynote that we heard this morning from Jan Stojka. The module then, we have to evolve the modules to treat incoming parameters as abstract data types as a way to shield the modules from the incoming external volatilities. Third, and perhaps most important lesson is that failure in digital agriculture is the norm and not the exception. So, for example, here we observed missing data due to sensor failures, networking failures, and human factors where sometimes people trip on wires and you lose the entire system. So in sum, errors can happen anywhere from the sensors all the way to the cloud. So this forced us to develop the idea of active digital twin to increase the system's fault tolerance. So one current limitation of this platform is that we cannot automatically migrate workloads between the edge and core clouds during permanent network outages, but we can tolerate intermittent failures. One avenue of future work we're exploring is how to enable scalable data analytics at the edge using an edge-centric version of Kubernetes in collaboration with IBM Research. So to recap, I gave you an overview of what digital agriculture is and data infrastructure challenges that are related to the state of the art in this space. I presented the design and implementation of Comosum, which is a reconfigurable platform to support DA applications, which we also call the software-defined or SDF. In terms of technical contributions, we distilled black box state-of-the-art systems down to classical ideas and into a single interface. We applied and advanced the state-of-the-art approaches to a new portfolio of system challenges that have not been seen before. And we showed that the system can be deployed across farm types and cloud providers and can tolerate intermittent failures. So then concretely, we described 18 months of deployment experiences with Comosum and their practical insights and limitations as they relate to extensibility to new digital agriculture vendors, reconfigurability in the cloud, and failure recovery. Comosum went through the full USENIX artifact evaluation and is available at the above link on GitHub. Additionally, I would like to acknowledge Ranvia Chandra, Elizabeth Bruce, and Tusha Chakraborty at Microsoft for providing us with Azure Cloud credits and guidance in deploying the FarmBIOS platform at Cornell. And the Comosum research was also funded by the US Department of Agriculture, or USDA, the US National Science Foundation, or NSF, and the Cornell Institute for Digital Agriculture. Now, thank you for your attention, and feel free to reach me at these addresses on the right, and I will now take your questions.